Hello, today we're going to look at assignment 7 of the STEP support programme, and this is the STEP question from assignment 7, which is a STEP question all about a polynomial. A couple of things to say about this question before we start. There are no separate parts, so there's not a part I and a part II, but there are several requests that are being made within all the text. And if you're faced with a question like this, it's not a bad idea to just start by highlighting every point where the question is asking you to do something. So we've got a show that here, we've got another show that. This says give a corresponding result. So that's another request, and here is find. And one of the things you can do is you can always indicate information in one colour and requests in a different colour, but as a bare minimum, just highlighting where the requests are helps make sure you don't miss out something that you're asked to do. Okay, let's have a look at the first part of the question. So in this question, it says by considering f of 0 or otherwise. So if a question says or otherwise, you can use different methods if you want to. Most of the time, a different method will not be any easier to apply than the method that it has suggested. So we have two different expressions for f of x. So let's equate them. It's meant to be an equal sign. K2 all the way up to x plus kn. And we're going to consider f of 0. If this question had not put in the other or otherwise, we'd have to do this method, but it actually turns out this is the easiest method to use. So f of 0, that means we're looking at x equals 0. So that's going to be 0, that's going to be 0. On this side, we're only going to get the an, because it's only the an that doesn't have an x attached. Then this bracket is going to become 0 plus k1, 0 plus k2, all the way up to 0 plus kn. And then 0 plus k1 is just k1, 0 plus k2 is just k2. So we have this, which is the same relationship as this one here. It's just written the other way around. So we can write as required, just to show that we know that we have done what we've been asked to do. So that's the first part of the question. Let's go on to the next part. Okay, this says show also that. That's often a hint that we want to do something very, very similar to what we've just done. So what we did before is we took x equals 0. In this case, if we look at this bracket and this bracket, then it looks suspiciously like we might want to take x equals 1. So let's equate our two expressions again. Just double checking I'm getting them right. X plus k1 dot 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 x plus kn. One of the things that you can do when you are writing solutions to STEP questions is you can start, as long as an equation hasn't been starred in actually the question, you can start, you could also use a dagger or some way of indicating this equation. Then you can later on say substituting x equals 1 in star, and you don't have to write out the whole thing again. I have written out the whole thing again. So this time, let's take x equals 1. So x to the n becomes 1. X to the n minus 1 is 1. So it's going to be plus a1. The next term, which isn't here, but it's going to be plus a2, and so on and so forth, plus an. And this side, we're going to get 1 plus k1, 1 plus k2, all the way up to 1 plus kn, which is exactly the same as this, apart from the sides are opposite, and these have been written the other way around. So I'm just going to say as required there. Now, the last part says give a corresponding result for. So we probably want to do something very, very similar again. And this time, if we compare these two brackets, it looks like we might want to take x equals minus 1. So let's do that. So here we're going to get minus 1 to the n. So if n is odd, this is going to be minus 1. If n is even, this is going to be plus 1. Then we're going to get A1 times minus 1 to the n minus 1, and so on. And I'm just going to write down the last two. So the one before this, we're just going to have 1x. So we would have had a n minus 1x. So we're going to have, instead of plus, it's going to be minus a n minus 1, and then it's going to be plus an. On this side, we're going to get minus 1 plus k1, minus 1 plus k2, and so on, minus 1 plus kn, which we can then write the other way around. Okay, so we now have three separate equations involving k1 to kn. We've done the first three requests of the question. Now it's time to have a look at the last part, which is probably going to be a little bit trickier. Okay, so for the last part, we're told to find the roots of this equation, given that they are all integers. So we know that the roots of the equation are integers. That means we could write this as something like this, if the roots were alpha, beta, gamma, delta. Noting that we've just got 1 x to the power 4, so this would give you x to the power 4. So that means that we can write this in the form, so I was just taking a bit of time to write all this out. We can write this in the form x plus k1, x plus k2, x plus k3, x plus k4. So k1, k2, k3, k4 are actually the negative of the roots. So we just need to bear that in mind when we get to the end of the question. Thinking about the equations that we had in the previous parts, that means that k1 times k2 times k3 times k4 is equal to 576. k1 plus 1, k2 plus 1, k3 plus 1, k4 plus 1 is going to be equal to 1 plus 22 plus 172 plus 552 plus 576. So 1 plus 22 plus 172 plus 552 plus 576. And if you add those up, you get 1323. And then the last expression we had was k1 minus 1, k2 minus 1, k3 minus 1, k4 minus 1. And it actually, it's slightly easier if we work from the back end. We know that this one was going to be positive. So we have 576 minus 552 plus 172 minus 22 plus 1. These two give you 24. These two give you 150 plus 1. So we get 175. Okay, so those are the expressions that we have for K1 to K4. We've got products of things which are integers. So it actually is quite helpful if we can factorize some of these. So 175 factorized to give you 25 times 7. So 175 is the same as 5 squared times 7. 1323, I know it's divisible by 9 because if I add up the digits, 1 plus 3 plus 2 plus 3, that gives me 9. So let's just divide that. 9s into 42 go 4, remainder 6. 9s into 67, 63 goes 7. So it's the same as 9 times 147. So that's 3 squared. 147 is the same as 3 times 49. So that's equal to 3 squared times 7, sorry, 3 cubed times 7 squared. And 576, what can I divide that by? I can certainly divide it by 4. So 4s into 5 go 1. 4s into 17 go 4. 4. Okay, so 576 is the same as 4 times 144. That's the same as 4 times 12 times 12. That's the same as 2 squared. 12 is 2 squared times 3. 12 is 2 squared times 3. So I'm going to get 2 to the power 6 multiplied by 3 squared. So looking at those 3 factorizations, this one has actually got the fewest prime number factors in it because it's got 2 5s and a 7. This one's got 3 3s and 2 7s. This one's got 6 2s and 2 3s. So this is the one that's actually going to be easiest for us to start with. Okay, I'm going to get a fresh page. So we've said that K1 minus 1, K2 minus 1, K3 minus 1, K4 minus 1 equals 5 squared times 7, which is 175. Let's assume, at least to begin with, that K1, K2, K3, K4 are positive. They don't have to be, but we'll assume they're positive for now, and we'll consider negatives in a second. And we can also assume that K1 is bigger than or equal to K2, is bigger than or equal to K3, is bigger than or equal to K4. Because if we swap around K1 and K2, it doesn't change any of these equations. We've just moved 2 of our brackets around. So let's assume that K1 is the biggest, and then we don't have to double count. Okay. 1, K2 minus 1, K3 minus 1. I'm going to make a little table, which is going to have vaguely straight lines, which is good. So the biggest that K1 minus 1 can be, if it's going to be a factor of this, is 175. And if it's 175, these all have to be 1. The next biggest it could be is if we took the 7 and one of those 5s. So if we did 7 times 5, that will give me 35. We've got a factor of 5 left. That's going to go to the next biggest root, and the last 2 are going to be 1. Then the next biggest that this can be is 25. So if we've got, take these 2 5s here, then this one's going to be 7, 1, 1. And then K1 minus 1 could be 7, which would mean these 2 have to be 5, and this has to be 1. And then this can't be 5, because if this was a 5, one of these would be 7, and we've said that K1 is the biggest. So those are our possible values of K1 minus 1, K2 minus 1, K3 minus 1, K4 minus 1. Now we can use those to have a look at what K1, K2, K3, and K4 would be. So if we add 1 to each of these, we get 176,222, 36,622, 26,822, 8,662. And we know that we need the product to be equal to 576. Okay, if we do 176 multiplied by 2, that's going to be more than 300, because this is more than 150. If we multiply it by 2 again, that's going to be more than 600, so that one's not going to work. This one here, we've got 36, and we've got 6, 2, and 2. 6 times 2 is 12, times 2 is 24, and 36 times 24 is got to be bigger than 600, because this is bigger than 30, this is bigger than 20. So that's not going to work. Similarly, on this one, we've got 26 multiplied by 8 times 2 is 16, times 2 is 32. So we have 26 multiplied by 32. That's bigger than 600. That one doesn't work. So we're really hoping that this last one is going to work. So this last one, we've got 8 times 6 times 6 times 2. 8 times 6 is 48. 6 times 2 is 12. So if we do 48 times 10, we get 480. If we do 48 times 2, we get 96. And then if we add up these 2, we get 576. So this one works. Okay, I'm just going to get rid of some of these. I don't want to get rid of everything. That's why this is taking slightly longer than I would normally take. Okay. You can also check the third equation, k1 plus 1, k2 plus 1, k3 plus 1, k4 plus 1 equals 1, 3, 2, 3. So if these are my k1, k2, k3, k4, this become 9 times 7 times 7 times 3. And so adding 1 to each of these. 9 times 7 is 63. 7 times 3 is 21. 63 times 20 is 1260. 63 times 1 is 63. And if you add these together, you get 1323. So they work in that equation as well, which is quite nice to know. Okay, so if they are all positive, then we have a solution that the k's are 8, 6, 6, 2, which means that the roots are -8, -6, -6, -2. Okay, let's get rid of some of these bits here. So we have one solution where all my k's are positive, which means that all my roots are negative. However, we don't know whether there are any negative solutions. So we do need to just consider that as well, which is what makes this more of a step question, because you do need to ensure that there are no other possible options. It's not enough just to say, okay, this works. I mean, it should work because you'd expect a unique factorization, but we better check. So using this result here, then we know that our ki minus 1, where I could be 1, 2, 3, or 4, has to be a factor of 175. So that means if we're going to, for our ki minus I, if we're going to consider negative numbers as well, ki minus 1 could be 175 or could be minus 175. It could be 35 or minus 35. It could be 25 or minus 25, and it could be 7 or minus 7. Oops, that's meant to be a 7. It could be 5, it could be minus 5, and it could also be 1 and minus 1. Okay, so that's a very long list, but those are all the possible things that could divide 175. That means that your ki's, this is ki minus 1, your ki's could be 176. We've actually all discounted that one. It could be minus 174. So remember that we're adding 1. Could be 36. Could be minus 34. It could be 26. Could be minus 24. Could be 8, minus 6, 6, minus 4, 2, or 0. So I think now that I have added 1 correctly in each place, it's slightly tricky because we've got some negatives and some positives. The other thing that we know is we know that the product of the k's is equal to 576, which I think we said is 2 to the 6 multiplied by 3 squared. So the k's have to only have factors of this form. So we can now eliminate some of them. 34 is prime. No, 34 isn't prime. 34 has a prime factor of 17. So this is not possibly one of these because I can't write it as 2s and 3s. So that one's gone. 26 also can't be written as a product of these. This is gone. 0 would cause us immense problems because I can't multiply 0 by something and get 576. So that one is gone. Which other ones can we eliminate? We can eliminate 174, I think. So if we divide that by 2, we get 87. 87 is the same as 3 times 29, and 29 is a bit of a problem. So we can eliminate that one. And 176 we can eliminate because 176 is the same as 2 times 88, and that's going to have a factor of 11 in it. Okay, so we can eliminate that many to begin with. I'm just going to change colour. So we can also look at ki plus 1. So 35, that's going to give me 37. Add 1 again. Minus 24, that's going to go to minus 23. This is going to go to 9. This is going to go to minus 5. This is going to go to 7. This is going to go to minus 3. This one is going to go to 3. So again, I'm hoping that I've managed to add 1 correctly in each case. The product of the K1 plus 1s was equal to 1323, and I think that was equal to 3 cubed multiplied by 7 squared. Double check, yes. Okay, so these k's have got to have factors which will go into here. So that means I can do some more elimination. So 37 goes, 37's prime, that also goes. 23 goes. 5 goes, because 5 is not in there. And that leaves us with 8, 6, minus 4, and 2. So my possible values of ki are 8, 6, minus 4, and 2. So up here, when we solved it for positives, we had 8, 6, 6, 2. So the only thing we need to now consider is, can we have a minus 4 as one of our roots? So if we have some negative roots, to get the product to be plus 576, they have to either all be negative, or 2 of them are negative, or none of them are negative. So if we have, or can we have minus 4 times minus 4 times minus 4 times minus 4? That will give me plus, but it will be equal to 2 squared times 2 squared times 2 squared times 2 squared, which is 2 to the power 8, which is not 576. Okay, so that's what we want there. The next question is, can we have one with a negative 4 times a negative 4? Now, if we have negative 4 times negative 4, to get 256, we need to have some 3s. So we need to have 3 squared. So we'd have to have 2 of 6 as well. So that is so that we get 3 squared in there. So if we work this out, we've got 2 squared times 2 squared. So we've got 2 squared times 2 squared times 2 times 3 times 2 times 3. That gives me 2 to the 6 times 3 squared. So this looks like it might be a possibility. So now we need to check that it will work in the other equations. So it works on this one. Do we know that if I take these roots, I will get 175 if I multiply my k I minus 1s. So these roots go back to these values of k minus 1. So I'm just going to put in a but there. If we do minus 4 minus 1, so minus 5 times minus 5 times 5 times 5 is equal to, or is not equal to 175, because we don't have the factor of 7 in there. So this is also not possible. So that means that the minus 4 cannot be used. 8, 6, and 2 are the only possible roots, and therefore I just clear what I've done. Therefore, the only values of k are k equals 8, 6, 6, and 2. Therefore, the roots are minus 8, minus 6, minus 6, and minus 2. Okay, so that, considering making sure that there are no other possible solutions, is a sort of step method that you need to be just a little bit careful with. It's not always enough to show that you have found a solution. You sometimes have to show that there are no other possible solutions. Right, well, thank you very much.